Hi everyone, welcome back to the second workshop in the Encode Worldcoin Educate series. Today we have a really interesting one on Orb Hardware and software, so I hope you're all excited. If you need to catch up on workshop 1, which was an introduction to Worldcoin, then the recording has been posted on the Encode Club YouTube channel, so do check that out if you missed the first workshop. I know there's a lot of new faces here today. So I am inviting our speaker up to the stage. Hi, Dan.
Hey, everyone.
Let me remove my stream and you're welcome to share your screen.
How's that?
Yep, looks perfect. I'll disappear off stage and the stage is yours.
Great. Thanks for having me. I'm very excited to get to present the Orb. It's a really fascinating and complicated piece of hardware and software. I assume most people here have already heard of it, and as was already mentioned, you can look at DC's introduction from Monday for more about like why we have an Orb, and I will quickly review that just for completeness, but he has a much more thorough introduction there. Also next week, there'll be more details on the biometric system. Though I'll touch on them, it's not the focus of this presentation. My goal is really to show you what's in the Orb and walk through the key parts of the software, and I'll step through the code towards the end. First off, as many of you might know, the Orb is open source, so all of the hardware and software I'll be talking about today is on GitHub, and we'll actually step through some of the source code in this repo. This repo has the hardware schematics. There are a small number of components that we rely on for security or fraud prevention that are not included in the open source repos. I'm happy to talk about those more in this presentation, ask comments in the chat. And we have an interesting design for how to isolate those components to make sure that they're not part of what the community needs to trust when they think about how to interface with an Orb. Okay, so first, what is the Orb? It's the verification device, the most secure verification device for a World ID as part of the Worldcoin protocol. Again, DC went into all the details. The very high level is that it provides a credential that can be used to prove if somebody uses this protocol, they know you're not a robot and you're not a dog. More realistically, you're not just an AI agent pretending to be a human, and you're not a human with many accounts on the same service. So though this doesn't work and this doesn't work, this should work exactly once per person. And then that credential can be reused without returning to the Orb in a protocol that at a high level looks like this and in more details looks like this. I won't go through all of this. The focus of this presentation is on this box here. But this is just to remind everyone that it's part of a much bigger system, which over the course of this series, we will elucidate. Okay. I'm not sure actually if the questions in the chat will pop up, but I'll take a break about halfway through to check on them. Okay, and then so that's the what. You might immediately have some questions. I think the natural ones specific to the Orb are here. These are the ones I hear most often. And the full answers are included in our frequently asked questions page and the white paper for the full details. I'll do the quick answers here. We use the iris and we use biometrics in general for scalability, inclusivity, and fraud resistance. So scalability means it will work up to and over 1 billion people. And for example, face or fingerprint biometrics don't work in that case. It's just simply not enough information in those modalities to get to 1 billion person scale. We also use iris biometrics and biometrics in general, because almost everyone has the ability to use the orb, even if they don't have, for example, a government ID or a bank account. And finally, iris is very hard to spoof. So there's a lot of information coming in through your eyes that the orb can use to make sure that it's not, for example, a fake eye or a modified eye. And that's not as true, for example, for fingerprints. Why couldn't we do this on a phone? Even if phones had good enough image quality, which many don't, there's also just a security question of how do we trust that the compute on a phone is valid, hasn't been tampered with. And so a large part of the requirements of the orb, which we'll get into, is for the compute to be highly secure. Another common question, of course, is what if the orb gets hacked? It is custom hardware, and you're trusting that the design of that hardware is secure. The long answer to that is included in part in the white paper, in part through the audits that we published, but the very high level answer is that the protocol doesn't fully depend on orbs being perfectly secure. There are lots of different layers to the security, and it's not, in that sense, a single point of failure. Also very important is that if you've signed up at an orb and then it later gets hacked, by design, your data is not at risk. And I'll show a bit of how that works soon. Number 4 is about where that data is stored if it's not on the orb and it's not on TFH servers for privacy. The answer is it's on your phone. And I'll also show how that works, how it's transferred, and how it's encrypted. Finally, because the orb is custom hardware, that means there's a manufacturer for that hardware, there's a team that designs it. How could that be decentralized? And how can a community of people build trust that the hardware is doing what it says it does? For example, all the things I just mentioned. And this is very different than other more common parts of trusting crypto projects where you have open source code running on a blockchain and a smart contract, and literally every step of that execution is available for everyone participating to see. So it's radically transparent, and there is no equivalent to that, exact equivalent to that in the hardware space, because these are atoms, not bits, and they're hard to, or nearly impossible to fully verify. And I'll talk a bit about the design of the orb and how it helps this, but the full answer is actually overviewed in the Advancing Decentralization section of the white paper. Just quickly check the chat. I'll try to cover some of these in the coming slides, but the quick answer is that we are using established methods for iris recognition. So there's a question about if we're using novel biometric iris measurements. Ours are novel in the quality of the image capture and the segmentation, which I'll show. But how we turn that into an iris code is actually using, quote, established techniques. I'll just skip questions that aren't specific to the orb for now and maybe get back to them later. I'll continue. Please continue to add questions in the chat. I'll check them from time to time. What does it take to make an orb? There's a lot more than this here, but this is the high-level overview. As I briefly mentioned, it's very important that you don't have to trust some external party or some server to have the images that the orb processed. These are sensitive pieces of data that are personal to everybody, and as soon as it gets uploaded to some server, you don't really know what it's doing. There's no way to really check it. So by design, the orb has the necessary onboard compute to do all the processing. And so the images don't need to be stored or processed on some server you have to trust, and they don't have to be stored in the orb itself. I briefly mentioned transparency and verifiability. Key pieces of this is that we want to be able to open source the hardware and the software, and that feeds into the design. We also want to support the ability for anybody to walk up to an orb and check certain properties of it. Examples could be that it's running the code that we say it is, which would be the open source code. Another example would be that it has the keys, the private crypto keys that the corresponding registry on the blockchain expects. And there's actually custom hardware in the device that holds private keys. And as we iterate on the orb design to make it more verifiable, we want to expose the ability for anybody to attest that the key an orb purports to have is actually on the device. I should also mention here that the way you could check that the open source code is actually running on a device, one way would be to actually take the memory off of a device. So walk up to an orb and pull out some SD card, and then check that the code that's on that SD card is what's in the open source repos. And the existing orbs don't have this functionality, but the next version of the orb by design does, which is something I'm personally very excited about. I already described that irises were chosen to be able to scale to over 1 billion people. And that requires not just using iris recognition, but actually having high enough image quality so that you can avoid having kind of false matches, is what we call them. So what if your iris looks pretty close to somebody else's? It's not identical, but it's close enough. We need the image quality to make sure that we can see those differences and we don't accidentally put you in the same bucket. In addition to the iris image quality, which I'll show examples of, we also need high enough quality for the face images. This is much easier, but because World App soon will support face identification as part of World ID 2.0, it's a fraud prevention measure. We locally compare the face of the user in World App to the face that the orb saw. And to do that comparison, the orb needs to have good enough face images, and you can see that in the open source code. Of course, we have to make the orb secure. I already discussed this a bit, but the way this works is we have extra sensors. It's not just a camera for the eye and a camera for the face, but there's actually 5 cameras, most of them looking at the face across different wavelengths, and I'll show these in a second. And that helps prevent the types of attacks where somebody might be messing with the orb or messing with their face to try to get extra world IDs verified. We also have tamper detection, so if you try to open an orb, there are sensors in there that can see that and deactivate the device. These crypto keys that I mentioned that are on the device, they're stored in something that's similar to a hardware wallet. So you can think of every orb as like a hardware wallet, and that lets us check remotely that an orb still has the key that we put on it in the factory. And that way, when the orb is talking to our backend or sending data from the orb to the phone, we have assurance that it's a legitimate orb. So this makes it hard to, for example, make a counterfeit device. We also have compute integrity. This is part of Orb OS. It's one of the features that we've built in. And this means that when an orb boots, it always boots exactly the same thing, and that is the kind of verified or signed, cryptographically signed source code that was built from the open source repos, and not something that somebody else modified. And this is how the protocol can be sure that the guarantees imposed by the actual implementation in the open source code are actually being executed on an orb. If it was easy for anybody to put their own code on an orb, then we could never trust the information that was coming off of it. Finally, of course, we're making lots of orbs, and we want to sign up the whole world. So it can't be that it has to be only experts can use it. It can't be that you need perfect lighting. It can't be that it works inside but not outside. So a lot of the design of the orb is actually just to make it easy to use in lots of environments and robust in case that there's some environmental stresses. This is the kind of evolution of the orb over time. I was lucky to have joined between this one and this one. And so I was around for this development, focused on the software and like bringing up some of these sensors. Some things you might find interesting is that the first versions of the orb actually had 2 cameras, so two lenses and 2 sensors, one for each eye. To save money, we switched to one where there's instead 2 mirrors. And so each mirror has like a direct view to each eye and can independently track them to get the capture. And for various reasons, including the ease of assembly of this contraption, we switched to a single mirror, and it will go look at one eye and look at the other eye. It doesn't have exactly as direct line of sight as this design, but it turned out to be good enough for our purposes. Zooming into that version of the orb, you can see, and this is the one that you've probably seen deployed. It has a chrome shell. We've made several thousands of these at this point, and so this is the orb as you know it. There's a front unit, and it has the four sensors that I mentioned that are on the face, and we'll zoom into these in a second. The tracking mirror, which feeds into a lens and captures the eye, custom infrared illumination, and there's a battery. There's a cooling unit with a fan to keep the main processor. And then we'll zoom into this main board in a second as well. Here's another kind of exploded view, just to give you a sense of what's inside. This is the lens that I mentioned, and the chrome shells. Okay, so now if you're looking just at the front of the orb, if you took off the shell, this is what you'd see. Here we have a face camera that is in the near infrared. So that's like just below, it's visibly what your eyes can see. If you go even further down in the frequencies of light, you get into the range that is considered like a heat camera. So it can see the infrared that's naturally just coming off of your body because it's hot. This is also pointing at the face. This is very similar to a front-facing camera on a phone. So it's a visible light camera, and we use this for getting visible images of the face as well as scanning QR codes. And this one's interesting. It's actually a depth camera, so you can see up to 1 centimeter depth resolution, the face. You could imagine that if somebody tries to cheat the orb by putting a screen in front of it like this that has a picture of a face, and or many other kinds of attacks, like a display attack, like a printout attack, it'd be nice to be able to see that there's a 3D structure in the face. And the main idea is that all of these sensors, these four plus the eye, can get combined using neural networks on the device to be very good at detecting when is there a legitimate human that's just trying to sign up for the first time versus somebody trying to trick the orb. And this is one of the main technical constraints of the device. It makes it complicated, it makes it expensive, but it sets it aside from all other hardware that's available in terms of being able to, on its own, tell if you're trying to cheat. This is the one side of the main board. We also have the other side. Some pieces I'd like to call out on this side is the kind of main microcontroller. And later in the presentation, I'll zoom into the software that's on here. We also have an SSD. And on the next version of the Orb, this is being removed for an SD card that's externally removable, as I mentioned. And then, as you could probably have seen in the other photos, there's these very large red supercapacitors, and these are used to buffer energy and then quickly dump it into the infrared illumination system that was here. That's these LEDs. We have 3 different wavelengths on this version of the Orb, and this is the flash. So the Orb is a camera, and this is the flash. It's actually invisible, mostly invisible, but it is a very bright light that ensures that we always get a consistent capture, no matter the ambient lighting in the infrared. And I'll actually show the code that uses that information in a bit. And then finally, on the other side of the main board, you would see the NVIDIA Jetson. We'll zoom into what's running on here later in the presentation. We also have lots of peripherals related to networking, like Wi-Fi and LTE. On this version of the Orb, we didn't end up using LTE, but the next one we will. We have GPS, though it's been spotty indoors, as you might expect. And yeah, on the top of the Orb, we have additional LEDs for informing the user, like the operator of the Orb, what its status is. And for the users, there's an external front-facing ring of LEDs. And if you've signed up at an Orb, you see it do this animation to let you know what stage it's in and that the capture is successful. Not. I think this is probably a good time to double check the chat for questions. Let's see. How can the orb verify it's from the original vendor and not a malicious one? That's a great question. I'll get to that in a second. Won't Orb's rescanning process lead to iris duplication? So this is a question about how iris codes work and get compared, and I'll also talk about that in a bit. And then there's a question about, can you just put an eye in front of an orb and not have face around it? And the answer is no. It's an important part of the design. As I mentioned, these sensors are combined to form a model of what's in front of the orb, and that model is highly specific to a legitimate use. And so an eye by itself, or an eye from a different animal, or a photo of an eye, or a fake eye, an eye with an artificial contact lens that changes its iris texture, all of that by design gets caught by these sensors and the corresponding machine learning system. That's a good question. It was also asked, how do you know an orb is legitimate and not malicious? It's not shown here, but there, as I mentioned, there's a hardware wallet or a secure element on each device, and it has a private key that is generated there when we manufacture the orb, and then there's a trusted step where the corresponding public key is put into a registry, and that registry will eventually be public or on-chain. And so then anybody could go up to an orb, and by asking it to sign some data with that private key, they can generate a proof that this orb is one of the ones that the protocol accepts as legitimate and not some counterfeit device. And that would work even if there's many manufacturers. It's a very tricky problem, but that's the plan. And then there was finally a question about iris duplication. If you get scanned twice, won't that cause some kind of duplication? The whole point is that you have a unique iris encoding, and that when the orb generates that code and sends it up to the service that checks uniqueness, if you've done it before, that service will say you're not unique. It'll block you, and then you won't get a verified world ID the second time. If I didn't answer the questions, or you have further questions, please put them in the chat. This is the lens that I mentioned. I have it here because it is one of the more interesting parts of the device, because it was custom tailored, if you will, for the orb to achieve as high iris quality as we can get for this use case, which is relevant for the distance that users are from the device, and the fact that we don't know that distance, so it has to quickly change its focus and track the user's eye. Interestingly, it's a liquid lens, so that means there's actually a piece of liquid in there that is actuated to change its shape, and that helps achieve the requirements that I described. This is a larger view of the tracking system with the lens and the mirror. So this mirror actually moves left, up, down, and the image of the eye comes in, bounces off these two mirrors, and then goes through the lens, and then it hits the camera sensor. This is the only sensor that's not in the front. So all of these 4 sensors are in the front, looking at the face. This is the entry point to that eye tracking system I just showed, and that sensor is on the back of the device. So 4 sensors here and 1 sensor in the back here. This is a comparison of the iris texture that you would get from an orb versus other iris scanners. And the main thing to know here is it's because the use case is different. So many iris scanners, they're designed to check that somebody is within some small set of existing people. So maybe you're trying to limit access to a very secure building. So you have the 100 people who are allowed to have access get their iris scanned, and then their iris becomes their password. So when they come into the building, they get scanned again, and you compare their iris to the 100 that are already there. So that's authentication, or matching the iris against a small set In the Worldcoin use case, it's the opposite problem. We have a very large set of existing irises, and instead of matching to that set to get into something, you're actually not matching that set. So to get a verified world ID, you have to have an iris that's not one of the million or one day billion that have already been registered. And it turns out, and this is detailed in full glory in the white paper and several blog posts, it turns out that this problem of deduplication versus authentication requires much higher resolution images of the eye. You need much more information in the eye to scale that up. And then I'll actually show more details about this in a notebook prepared by the Biometrics team, but this is just a quick overview of what's happening. So after the iris image is captured, the orb locally converts it into one of these codes. And then these codes are what are used for checking uniqueness on the back end. Very interesting work recently happened to make this even more secure, where actually the code is broken up into 3 different parts and sent to different servers to do the uniqueness check. And interestingly, we have the property that any of those individual servers actually don't see any information about the iris code. So the 3 parts individually provide no information about the whole code. Only if you had all 3 could you recreate the original code. And even though that's true, they're still able to collectively check uniqueness. That's called the secure multi-party computation design. And there's recent blog posts and even an explainer video from Remco about how that works. So if you're interested in like how this part could still remain private and secure, check that out. Okay. Now that's a really quick overview of the hardware. If you have more questions about the hardware, please throw them in the chat. I'll quickly check that. The next section I want to go through is software, which is what I work on more closely. But let's see what's in the chat. Has any government shown interest in having orbs for their own country? The answer to that is yes. And there was a recent publication related to the NEMOS project in Malaysia. The specifics I'll let you read about, and there'll probably be more information coming out soon. But this is in collaboration with the government. Let's see. Is the private key generation code open source? There's actually no code in a sense for this, or at least none of ours. So the hardware that generates private keys, similar to in a hardware wallet, it's not that you generate a private key and then you put it on the orb. Actually, this piece of hardware generates it internally, and then it only sends you the public key out. So by design, nobody ever sees the private key. And so, yeah, there's really low-level hardware and maybe embedded code on that chip that generates a private key, but that is not open source. The design for the secure element is not open source. Patients with cataracts or other diseases that cannot verify the iris. That is true, yes. So there's some people where iris recognition will not work. We try to make it work for as many people as possible. So we do through like purpose-built data collection experiments and through users donating data through World App. We do have a whole team that looks for kind of edge cases and sees which ones we can still make work. But there will be some people where it will never work, and the protocol has to adapt in the future to find a way to allow them to still use World ID without going to an orb, at least in the same way as we have it today. That includes pirates. This is a great question. Can you track people on the application layer based on the data from the orb? The answer is no, and it's a bit outside of the scope for this presentation, but if it's not, I mean, and I think it was at a high level covered in DC's presentation on Monday. But the short answer is that the zero knowledge proofs that World ID use make sure that it makes sure 2 things. One is that the data from an orb is never linked back to the World ID itself. So when you verify with some service with World ID, they can't know which iris code that corresponds to. And then secondly, if you do that across many services, you can't even track that same world ID across those services. And I think the World ID docs are probably the best place to look for more information on that. The sensors are off the shelf. Maybe in the far future, we'll think about customizing them for maybe better security. Can the orb tell if someone's wearing contact lenses? Yes. That's one of the requirements for the orb, because there are some contact lenses that change the texture of the iris, and we need to be able to block those people and say, please take out that contact lens, because we wouldn't be able to see their real eye underneath. And so that there's a combination of having very good imaging and custom machine learning systems running on the device enable that kind of detection. What if you generate irises with AI? So that's a great question. You would still need to somehow convince the orb to accept that iris. As I already mentioned, there's many sensors on the orb, and they're all integrated into one system that checks that the user is legitimate. So it's not just about having an iris pattern, but having a real live face and a real live eye. And there's a lot of information coming out of your live face and live eye, besides the iris pattern that the orb is looking at, to make sure that you're not cheating with AI. And so the answer to what mechanism will the orb use to address this is it's the same mechanism that the orb is already using to, for example, detect contact lenses. And that is that, yeah, you need more. You need to not just generate the whole eye, you almost need a new human. That's the idea. There's a separate part to that, which is what if you can somehow bypass all of the sensors and somehow inject the iris pattern right into the computer on the device or change the software on the device. And that goes into the compute integrity mechanisms I described before and the tamper detection, so that it's hard to modify what's inside the orb. And that one I already answered. Keep them coming. Love it. So yeah, moving on, we're about halfway through to software. So this is something I work more closely on than the hardware. And we have a team of roughly 12 people at this point focused on all the software inside the device. Plus a whole separate team that works on the neural networks on the device. And as I mentioned before, it's open source. And so actually I'll step through the code and I'll be looking at repos that are publicly available under MIT and Apache permissive licenses. We already did this actually. So there's a much more kind of technical deep dive that'll go into way more details than I'll do in this presentation. But if you're a software engineer or want to be a software engineer, or especially if you're interested in Rust, there's a roughly 45-minute walkthrough that I did with Anastasios, Valentin, moderated by, it looks like this. And so we walk through all the different code that is used for doing a sign up. And so actually a lot of this code I'm about to step through here. But first I want to show what's actually inside. We have a Jetson Xavier NX. So that's actually a chip that has both a CPU and a GPU on it. It's called a system on a module. Key, it only uses 20 watts. And so like GPUs that are used to train models like ChatGPT use 50 times more power than this chip, but it's still enough to do real-time image processing for the fraud detection that I already described and for the iris encoding. And I'll actually show different steps of that in a notebook in a second. We built a custom operating system that's based on Ubuntu and Debian Linux distros, and it has some of the features that are required for the security in the orb and for verifiability. In parallel to Linux, there's a real-time operating, there's a trusted execution environment. So this is a much smaller and easier to verify operating system that is designed to run secure code, and that's inside of a secure enclave on ARM. This is an ARM chip that's called Trustzone, and on Intel it's called SGX. And this is the name of the OS that's running in the Trustzone environment. What's special about that environment is that there's a lot less code, and there's way fewer places where there could be a bug that would let somebody hack the system. And B, it has actually special hardware access to secrets on the device that Linux can't see. So that means you can use it, for example, to encrypt other keys or encrypt parts of memory. And that's if somebody hacked Linux completely, they still couldn't decrypt those pieces of data. And then on the Jetson, most of the code is in Rust, and we'll see some of that. The interfaces to some of the machine learning models are in Python. Inside of this trusted execution environment for security, we have applets written in C. And then NVIDIA provides a framework called TensorRT that allows compiling the neural networks into a form that's efficient for this device. And we leverage that to do the inference on device. And all of this is under this repo, open sourced, except the machine learning models, which are in separate repos I'll show you in a second. Additionally to the Jetson, we have two microcontrollers. One is the kind of main MCU that is talking to most of the peripherals on the device. That includes things for the user interface. There's a button on top, there's LEDs that I showed before, there's speakers, and it's managing the power and data for all of these peripherals. It also talks to the Jetson and the other microcontrollers. It has the GPS data coming in. We have temperature sensors and voltage sensors to make sure the device is healthy, and this microcontroller will turn things off if things go out of whack. And then critically, it can do real-time triggering. So we want to be able to control in software exactly when each camera is triggered. Maybe, for example, you want the illumination system to be running at 30 hertz, but then you want to trigger another camera just in the time between those flashes, so to avoid interference. And that's done by using external triggers to tell each camera or each LED when it should flash or when it should do the capture. There's the lens that I mentioned, and it has a low-level feedback loop implemented on the main microcontroller to keep it stable, and then a higher-level feedback loop to do the actual autofocus on the Jetson. There's the 2D tracking for the mirror that I mentioned, and the interface to that is all done through this microcontroller. And if you want to see what any of this looks like, it's also open source in this Orb firmware repo, and all of it's written in embedded C. There is a second one, so this has 2x ARM Cortex M4s. The second one is the interface to the secure element and the tamper detection system, which I won't go through now, but for example, it has features that allow detecting if the orb has been opened, and it has the interface to use that secure element for signing or attestation, which, as I mentioned before, can be used to check an orb isn't counterfeit. It also can be used to allow the backend to know that it's talking to a legitimate orb. At this point, I wanted to really quickly flash some code just to show anyone who's interested where it is and what it looks like. The first place to look if you want to learn more about the code on the orb is this blog post for when it was open sourced back in March of this year. And we tried to give a high-level overview of the compute, which I just went through, and a tour of the code. So along with this video, there is like a really high-level flow outlined in the blog post with links into all of the different parts of the code that are relevant. And I'll show some of them now. So this is the starting point. It's the Orb software repo. And the code I'm going to go through is actually all inside of Orb core. So you can click through and you'll see it here. And so everything that's related to capturing the images, processing them into iris codes, signing those iris codes, encrypting the image data, sending it back to World App is inside of this kind of main application on the device. And you'll see each of these steps in the open source code. So here is like one of the high-level entry points for doing a sign-up. That's why it's called do sign up. And I think it really reads like a high-level flowchart of the main thing the orb is doing. So after some initialization, the first thing that an orb does when you press the button We have two right now. So one is to unlock the orb from the operator side. So the operator of the orb shows a QR. And the second one is the user QR. And this is used to pair the user's phone to the data that's on the orb so that it can be encrypted and sent back to that phone. This is also how we then later know that the World ID private key that the user generated on their phone is the one that should be verified or verified if they pass the uniqueness check. So there's some critical data we get right up front. I'll move on to this step. So here's where all the cameras get turned on. And you can see that here. So we're enabling the cameras themselves. We're also enabling some neural networks to process the data from those cameras, and some internal agents that are doing things like moving the mirror to track the eyes, or changing the mirror focus to get a sharp image of the eye. And this one is changing the LEDs to make sure that the eye is the right brightness. And as that data comes in, it gets processed through these handlers. There's one that handles the infrared data, really the output of the infrared neural network, or the network that was trained for infrared data. And here is like a key part. So we have the image that came in. It has a score that the neural network assigned of how good it is. And if it's above a certain value, which is here, then it's good enough to continue. It means like we found a sharp enough, high quality iris image. And we additionally check that the brightness is right. And if these two are valid, then all of this data gets packaged up into the output of the biometric capture, which is here, and gets sent to the next stage, the pipeline. This is imaging, take the picture, and this is process the picture. And we'll look through a really great Google Colab hosted Python notebook that the AI team prepared. And this will be a large part of the focus of next week's presentation on biometrics. So I won't show exactly how each step works. That'll be next week, or sorry, in the next presentation. But I will just show the output so that you can see what's done in that step. So the iris has already been captured as part of the whole eye image. And the first thing is to figure out which part of that image is the iris itself. And this is actually, it turns out, one of the hardest parts, because there's lots of different types of eyes, lots of different ways that they might be partially occluded, like by the eyelash here. The pupil can be different sizes. There's all kinds of reflections and rotations. So it's very important that the AI can tell exactly which pixels are, for example, eyelash, and which pixels are iris. And a lot of work goes into training the model that can do this. And again, everything I'm showing is part of the open source code. Then, once the iris is detected, we do at this point all kinds of fraud checks, like in the chat it was mentioned, the contact lenses. So this would be the point where we're also checking in parallel that there's nothing fishy going on. Maybe it's a picture of an eye, maybe it's a display, maybe it's a contact lens. And then we actually have to pull out the iris itself. And so these parts here are the unwrapped version of these sections here. And so it's like turning the circle into a rectangle. And then that rectangle gets processed. This is something called the Gabor method. And I mentioned before, it was asked in the chat, do we use existing techniques? And yes, this is an existing technique. We've highly fine-tuned it for our use case, but it uses something called a wavelet transform, which is in the class of frequency, domain, or spectral methods. What that means is it's looking at patterns at different scales in this picture of the eye, and extracting information from those patterns that is highly robust to all kinds of other transformations you might imagine. For example, if we got the same picture but it was slightly brighter, or if we got the same picture but the eye was slightly more closed, or the pupil was slightly larger, or it was rotated, all of those have to be accounted for in the method that goes from here to here, and in the method that compares these codes to other codes. And so when people talk about the orb hashes your eye, this is what they mean. So it's taking this photograph of an eye and turning it into one of these unique codes. And then it's not done on the orb, but the next step is, of course, sending these codes up in a secure manner to be compared against all previous codes. And so if that step passes, that's when you have a verified world ID. Great. And then last but not least, this is my favorite part, the output of the pipeline, which has these iris codes in it, is used both for detecting frauds. This is where, for example, the contact lenses are checked. And we pass it to upload self-custody images. So here, the iris code and the corresponding images of the iris and face from basically all 5 sensors you can imagine are packaged up and critically encrypted. So encrypted and signed. So this last step here is encrypting the entire package with the user's public key, which came in through the QR code that the user showed. So this is generated, the corresponding private key is generated in World App on the user's device. And so the overall package is encrypted with the user's key, such that if that package ever leaked, it's only the user, or if it was, in this case, uploaded to a backend to get it to the phone, even though that backend sees the encrypted package, because the user owns the private key, it's basically garbage data. Nobody can see these pictures except the user. And so that's the most important point. You can also see that some of this data is double encrypted. So in this case, it's actually the raw photos. The iris code itself and the face vector are not double encrypted because they're actually used later by the user's phone. But the raw images, which right now we don't have an explicit future use for, but may in the future, are also encrypted with a key that is stored by the TFH backend. This is an additional security measure so that even if both your self-custody package and your private keys got leaked, maybe your phone got hacked, your actual raw biometrics are still protected. And that's basically it. If you look at do sign up, it's the end. This last step is just sending all that data, sending the iris code specifically to the uniqueness service that I described. And I'm skipping over it because, interestingly, this is moving. So this step is currently done on the Orb. That's why it's here in the open source code. But it's moving to be done in World App. And that's because actually it helps decentralize the protocol to think of the Orb just as a camera that takes images, processes them, and sends them back to you. And then anything else that has to interact with the protocol, sending the iris code up for a uniqueness check, can be done from World App or basically from the user's device. And that reduces the kind of trust that you need to have in the Orb itself. I'll double check the chat for questions.
We've actually got a load of questions in the questions tab, which are easier to find you at the bottom of the screen.
Got it. I didn't see that. I was looking for it before, but didn't see it. I'll get to both. The subject can be moving a little bit, but the Orb doesn't ask it to change its eyes, it doesn't ask it to blink. So you're just in front of the Orb and it captures your eyes. There's no specific thing that you have to do. The source code is online, so I'll post the links at the end, but it's the Orb software repo. And you can see kind of all the details in this blog post that we posted here. How can someone access my iris codes? If you mean, can you access your own iris codes? Technically, the answer is yes, because they're on your phone. We don't right now expose an interface to that because there's no use case for somebody to do it. But in the future, you might imagine there's lots of apps that interface with the protocol, and some of them might support inspecting the biometric data that you have. They're probably not that interesting, but if you really want to see your iris codes, technically they're on your phone after you sign up. Thanks for the link to the Colab notebook. Let's see. if somebody loses their private key, great question. I actually have this in the end. And why does it have 3 wavelengths? So I'm just going to check how much time we have. We have 4 minutes, 3 minutes, and just look at all the questions. I'll try to get through as many as I can. So very quickly, if you lose your private key or you lose any of the data associated with the sign up, in the future, hopefully soon, there will be a reset flow where you can go to an orb, and instead of doing a normal sign up, you do a reset where your original public key and associated world ID gets deactivated and you get a new one. And this is fine because it's just important that everybody only has at most one verified world ID. And so as long as we can, by matching your iris code back to the original world ID, delete it, the public component of your world ID is matched to your iris code, not the private component. And so we have the ability to delete or deactivate the original world ID and generate a fresh one. And related to that is because your world ID isn't a login, it's not like a password, you're just using it to prove humanness on top of some other login. So if you use it for Twitter, you'd still have your Twitter login, and then there would be this extra step where you could prove you're human. By losing it, as long as you can get a new one, you still have all the access you previously had. We have 3 wavelengths because we wanted to build the orb to be as general as possible, and we didn't know 100% what we would need in the future. And one of the ideas was that you could get much more information out of an iris if you image it across 3 wavelengths than if you only have 1. And that's still in research, but the next version of the orb only has 2. Iris recognition ML is open source, but the model that's open sourced was not trained on the same data as the real model, but all of the code is open source. And that's actually what we were looking through. So this notebook is part of the Open Iris, part of this repo. And you can see exactly how both how the model works and how to use it. Let's see. I'll stop sharing for now. So are you allowed to change the iris in the software, for example, with bugs? I'm not sure what you mean, but if the software was not faithfully converting an iris into an iris code, that would be a bug, and it would break pretty fundamentally the protocol, because then if somebody signed up twice, it probably would allow them to have multiple. It's one of the reasons it's important to have all of this open source so all of us can check it. Can you get fully functioning orbs to do research on them? DM me, I guess would be the answer to that. I'll put my credentials in the chat, my email in the chat at the end. An individual doesn't be able to check. We already answered that one. When can I buy the hardware? That's a great question. We're working on this. So right now, orbs are not for sale, but they're rented. And people get paid in the Worldcoin token for each person that they sign up. But we are hopefully going to transition to a model where people can actually just buy the orb. And I don't think we have any publicly available dates for when that will be, but soon TM. If I didn't answer your question, now's a good time to scream, but I think we're out of time. So my email is here. Let's see, didn't work. That's my email. I'm very happy to answer any more questions that come up later. Also, for the record, the name I forgot before is Miguel. Miguel did the interview previously for the walkthrough of the orb. So if anyone wants to know more technical details of how the software works specifically and dig into the functions and the infrastructure and frameworks that I just really quickly flashed, go check out the previous video that we had where Miguel interviewed me, Anastasios, and Valentin. It's about 45 minutes, and it's in the open sourcing blog post, which is the main link I want everyone to take away from here. And it's that link. Cool. Thank you, everybody. Thanks for the great questions. I hope this made some sense. And like I said before, feel free to reach out to me for any future questions.
Thank you so much, Dan, for that talk. We've had loads and loads of questions. I did actually remove some of your questions from the chat so that we could get through the relevant ones, but do come along to the rest of the workshops, because I'm sure in one of those you can ask your question to another speaker who will be able to answer it. But we had so many, we couldn't get through all of them. So sorry about that, guys. We'll see you next week for our next 2 workshops on Monday and Wednesday. I'll send you the calendar invites this week so you'll know when they are, but they're at the same time every time. So thank you so much for joining us, everyone, and have a nice rest of your day.
Thank you. Thanks, everyone. Bye.